So what I'd like to do is go over the types of things that I want us to be able to do, um, at this stage. So normally this midterm that you see, I think you can see the midterm in front of you, right? Okay, good. So this is a midterm from summer of 2018, but then there are also midterms throughout kind of throughout the years, I suppose, throughout the semesters that are available um, on our shared Google Drive. So let me kind of switch over for a quick second to direct you to those. Um, so if you go to our shared Google Drive, what you're going to see, well, first let me do this. I'm going to bring up the syllabus because that has a quick link. Just as a reminder, there's a short link that's here, GOO.GL, and then 8WH1RD. So this is also on the Canvas kind of syllabus module or area, that syllabus page. You can get it there if you don't have it. But that's where I am right now. I'm going to kind of stay here for a second and show you, or at least remind you, that in here, at least where there's a kind of a figure here, these other ones are, there's nothing in there, but so those are hidden in assignments and labs. So I've been using Canvas for that. But if I drop into this exams and the midterm area, what you should see is midterms such as this for 18 spring, the key, and then a blank midterm. So you'll see something like this that's blank, and then you'll see the version of it that has a key, which is great for allowing you to practice several different types of problems. And so you'll see it for 18 summer, 18 fall, 19 spring, and 19 fall. So the one that I just want to take a few minutes looking at is going to be the one for 18 summer I'm going to bring up. So I'm going to switch back over to that one. Let's see. And so that one looks like this. So that's the one thing that's probably the most important thing that I'd like for us to be able to do today is spend some time looking at that. So questions or thoughts on anything before we kind of dig into this? And I'm also, well, I'll just present that. Are there any questions or thoughts on anything? So this that we're looking at, normally it would be timed and it would be 75 minutes. I think what I've set up on Canvas is that it's going to open up on Thursday at noon and be due by Friday at noon. So make sure, so you could start on it Thursday at noon, or you could start on it Friday morning. Usually, if we're in a face-to-face environment, 75 minutes is more than enough time. Some might finish it in 45 to 50 minutes. So it's not a long midterm typically, but the circumstances are a little bit different here. So you'll have more time to work on it, but it should be more than enough time in some ways, but then there's still some learning that's going on as well in the process. So because we're seeing some of this stuff in such a fast pace, the additional time should benefit you. And also by your looking at some of this today, it'll give you a chance, and it's really important that you look at this and a couple of others today, that you get a chance to ask questions, get some practice. Today, Wednesday, and then tonight tomorrow morning, maybe schedule an office hour if you have questions about something tomorrow morning. And so that's why I set it up for kind of this after tomorrow afternoon. So that gives you all of today and most of tomorrow to take a look at it and to ask some questions. But I do realize all of this is going a bit fast. So I'd like to spend a few minutes looking at the types of problems, and I know that there's going to be some, an introduction of some new ideas as we talk about this. So be sure to either ask, drop a question in the Zoom chat. I'll try to keep my eye on that as we progress through this, or just, feel free to, just holler out with some thoughts or questions. So hopefully you're looking at what I see right now. I think you can see that. So some of the basic things we've looked at, and hopefully some of the practice that you've been able to get on Canvas with these participation quizzes will help you see what, help you approach these problems. So the first one here asks you to represent a hexadecimal value using binary notation. And it says that it's assigned 2's complement 16-bit value. So it is a 16-bit value. Each one of these hexadecimal values requires 4 bits. So because there are 16 different hexadecimal values that range from 0 all the way up to 15, you need at least 1, 2, 3, 4 bits to represent all of the different hexadecimal values from 0 through 15. So each one of those 4-bit chunks is a nibble. So there are indeed 4 nibbles that are here. So 4 times 4 is going to give us our 16 bits that we're looking at. Let's go ahead and represent each one of these as a binary value. It works out that if I were to take, for example, a number that's hexadecimal, and let's say that the number, I'm going to use a much smaller value. I'll use a 10 and a 2. So you have a couple of different ways, and this is important. You have 2 different ways of converting this hexadecimal value to a binary or a decimal value. So since this is A2, and each one of those is a position, has a value, a multiplier rather, 16 to the 1 would be this one, and just this would be 16 to the 0. And this kind of increases. If there had been a third one, it would be 16 squared and so forth. But I just have 2 hex values. So this is how we're going to do this simple conversion. We're going to turn this A back into a 10, and then do the multiplication suggested, and then 2 times 16 to the 0, which is just a 1. So this hexadecimal value is going to be 160 plus 2, or 162 in base 10. Now, that worked out. This is something that we saw a few weeks ago with doing the conversion in any given base. As long as you know the base, you know the multiplier, and whatever that radix is, or the base, it just kind of, you keep multiplying each one of those values to that base raised to a power. Here's where it's slightly less intuitive. If I take my A, which we've said is 10, I know that a binary 10 is going to be 1, 2, 4, and 8. So 1, 0, 1, 0. There's my 10. I also know that my 2, let me get my multipliers up top, 1, 2, 4, 8. My 2 is represented like that. So I have juxtaposed, I suppose, the A, or the 10, and the 2. And if you take this information that we have, even though we wrote it as 2 separate binary values, I can also look at this 1, 2, 4, 8, 16, 32, 64, 128 as one big binary value. So that means that we have a 128 is what this is, and we have a 32. A 128 and a 32 is 160. And then if I look over here, it looks like there's only a 2. So we have a 2. So we still get 162. So that one big binary value is 162. So you have a couple of ways of kind of doing this conversion for these hexadecimal to binary, and hexadecimal to decimal. So that means then when we look at the original value that we have here, the 9, the 0, the 2, and the 10, I know that a 10 looks like this. So it's because it's 1, 2, 4, 8. 8 and 2 is 10. And I'm going to do the same for each one of these. I know that a 2 looks like this, and of course a 0 is this, and a 9 is this value right here. So that is the binary representation of this hexadecimal value. That's my 9, 0, 2, and 10. So now I have a choice. I can convert this, if I can bring my eraser. I can convert this to a decimal value if I want. I'll do that in a second. Or I can even convert it to a hexadecimal. So similarly to what we've, with hexadecimal values needing 4 bits, octal values, or base 8, it goes 0 through 7, and it only uses 3 bits. So every octal kind of digit uses just simply 3 bits. So this, so how do I get 3 bits from here? I don't know how to easily, well, there are ways of turning this into an octal value. I could do something that involves division by 8, look at the remainder, division by 8, look at the remainder. What I'm really kind of expecting you to do is to keep it a little bit simpler. Just like any, as we did before, 1, 0, 1, 0, 0, 0, 1. Oops, is that 1, 2, 3, 0? So just as we did with any binary number, I can always split it up into a hexadecimal. Just grab 4 more, and I have my 2 hexadecimal values. But similarly, I can also take this 1, 2, 3. I'm looking at this one here. 1, 2, 3, 1, 2, 3, 1, 2, and we're just going to have to populate that with a 0. So as a hexadecimal, as an octal value, I can do some, I can convert this into an octal where this is a 2, this is 1, 2, 4, this is 1, 2. So as an octal, my value that I started out with, my simple, smaller value of an A2, and we're just doing this before we come back over here and look at the larger value. We can represent any binary value as an octal. Start from the right, going to the left, grabbing it in chunks of 3. If I had started from the left, going to the right, I'd get 1, 2, 3, 1, 2, 3, and you'd have problems with what this value represents. So you will end up getting an invalid value. So let's just do a check. Remember, we said this is supposed to be 162. Is there a 1 at the end of the binary 9? This is absolutely, this one was a mistake. Thank you. This should have been a 9, or 1 over here is the question. So let me erase this, thank you, and drop in a 1. So that gives me 1, 2, 4, 8. 8 and 1 is 9. Perfect. Good, thanks, Alex. And then if I go to my 242, remember that each one of these is a multiplier, holds a certain position and a weight and a magnitude. So 242 times 8 to the 0 times 8 to the 1 times 8, 2. So I can do a simple conversion of this base 8 value. And so that looks to me 8 squared is 64 times 2 is 128. 4 times 8 is 32. 2 times 8 to the 0 is just a 2 times 1. There's a mistake in here somewhere. 2 times 1 is a 2. So let's make that a 2. So now when I add this up, 8 and 4 is 12. 6, and then this one is just 162. So we still get 162 whether we show this, whether we are using base 8, base 10, or base 16. Of course, it should still represent the same quantity. Right? It should be 162 regardless when we look at its base 10 representation. So how does that help us? It means now that if let's see if I can change this a bit. When I look at, I think I can blow this up a bit. So now when I look at this and I want to change it into an octal, what I'm going to do is grab those three, 1, 2, 3. And let's see where we are. And then 1, 2, 3, 1, 2, 3, and then this one will be populated with zeros. So it looks like then as an octal value, I see a 2, I see a 1, 2, 4. So this one is a 4 plus a 1, that's a 5, a 0, a 0, a 1, and then a 1. So as an octal value, this is going to be a 1, 1, 0, 0, 5, 2. Let's write that. 1, 1, 0, 0, 5, 2 as an octal value. Questions? All right. So how do we turn this into a decimal? Well, there are a couple of things to consider, and you'll see examples from previous midterms that sometimes it's a negative and sometimes it's a positive value. So on the lectures that are there, we get more into 2's complement representation, but complement notation takes a range of values, 1, 2, 3, I'll just use 6, 7, 8, and 9, and it really takes 1/2 of those values and says, here's the complement. So we talked about 9's complement, and the complement really would be those values that complete or bring these values here up to, in this case, it would bring it up to a 9. So 4 and 5 are complements. So these are kind of like the negative numbers on the right side. So we split half of our data set so that we can represent an additive inverse. So these are 9's complements. And if I add 1, I'll get a 10's complement. So really, the 10's complement is going to be the 6, the 7, the 8, 9, if I add 1 of those. And the reason that works, or that's the case, if I say 4, and then if I add my 5, which is the additive inverse, I certainly get a 9, and then if I add 1 more, right, I could have added it here, but I'll add 1 more and I get a 0. So we're just trying to get a 0 result with our additive inverses. It splits this area in half. So additive inverses means that we end up taking our space and kind of splitting it in half. So if I had 3 values, 3 binary values, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, and then a 6, and 7, we're going to end up also splitting our binary representation, like that range of values will be split in half. Notice that whenever you take the complete range of binary values and split them in half, it must be that half will have zeros and the other half will have ones. That's how we know that these values are our additive inverses, just as we did before. And if we add 1 to these values here, so these are our complements. And if we add 1, it becomes our radix complement. So these are kind of our diminished radix, like a 9's complement, diminished by 1. Instead of a 10, it's a 9. These are our complements down here, diminished by 1. So if I add those two together, I'll get 1, 1, 1, just like we got 9, 9, 9. And if I add those two together, I'll get 1, 1, 1, similar to the way we got 9, 9, 9. So these are complements. They complete it. They take it up to the, like the 9, 9, 9, we take it up to the 1, 1, 1. And then the pattern is that to get the 1's complement, you really just need to invert all of the bits, and that gives us our 1's complement. So if I have a number, such as, I'm going to go over here just because there's some space, 0, 1, 2, and 3. So if I have a number 3 in base 10, the 1's complement of 3 is a 1, 0, 0. So if I just simply invert the bits and add 1, so I'm going to go ahead and add 1 right here, I get what's essentially the additive inverse. So this is a -3. My negative values will always have a 1 out front. If we've decided to interpret and look at these as a 2's complement or through the 2's complement lens. So this is a negative value. When I add these up, 1 and a 1 is going to give me a 2. 1 and a 1 will give me a 2. 1 and a 1 will give me a 2. And then we have an extra bit that carries out. And since we have a 32-bit register, there's not going to be an extra bit that's there, but it may be saved in another kind of area that computers use. It could have a flag. It could be saved elsewhere to indicate that yes, we did overflow or carry out. So we do get our 0. We have the ability to work with these values that now allow us to consider these numbers negative. So we have additive inverses through the method of complements. So this number here, for an example, if I gave you something like this, 110, and I said, what is its value? You don't really know what this value is. Is it, let's see, 1, 2, 4. Is it a 6? Or is it a negative value? And I have to tell you one way or another that it's either signed information, that it has signed information there, or it doesn't. And if I say use the 2's complement lens, that means that it's signed. So this value, since I've said that it's signed, then I know that this automatically is negative. The 110 is automatically negative. In order for me to figure out what this value is, now that I know that it's 2's complement, I'm going to go ahead and say, oh, it's a negative number, and get ready to write the answer down here. So what is the magnitude? In order for me to know the magnitude, I have to kind of undo what I did before in some sense, but the magnitude is going to be determined by my flipping each one of those bits and adding a 1. And so this is going to be a 2. So in order for me to get the magnitude, I'm going to have to do that. I'm going to have to invert the bits and add 1. And so this is a -2. Now, you can double check. If I take my -2 that's here, 110, and add to him a +2, if I did it right, I should end up with 0, or at least 3 different zeros here at the bottom. So 0 and 0, 1 and a 1 is a 2. So take this and carry the 1. 1 and a 1 is a 2. And then there's a carry out that gets dropped off. So it works. This is our version of a -2. So let's go ahead and undo some of this that we've seen. Maybe just erase this. So we have this ability to look at numbers and determine if they're positive or negative. Since each hexadecimal value has exactly 4 bits, the space that we're going to work with here when we're working with 4 bits, let's do this. Hexadecimal values, there are 16 different characters, and they go up from here all the way to 1111. The easiest way for me to write down all of these, I know that there's a pattern. 1, 2, 3, 4. 1, 2, 3, 4. Splits it in half. And then this one goes 1, 2, 1, 2, 1, 2, 1, 2. And then This one goes, so 1, 2, let's make sure, and then 0, 1, and then this one is a 2. Let's make sure I'm doing this right. 1, 2, 4, 8. This is, oh, I'm missing something. I only did 8 of these, and I need 16. So I need 16, so that's the mistake. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have 16 different values to work with. Now it goes 1, 2, 3, 4. So those are 8, and then it reduces 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then every 2, 1, 2, 1, 2, and then this one is every other 1. And I'll have to clean this up down here at the bottom. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then 3, 4. So if you look at all of these numbers, if there are no mistakes here, you should have the values anywhere from 0. That's a 1. Let's see, is that a 2? Sure. That's a 3, 4, 5, 6, 7. And then over here is an 8. If you double check this, you should see that all of these values add up. And then 15 is the largest. You could do it manually by just kind of going through it, but there is a pattern of 4, or rather 8 and 8, 4 and 4, 4 and 4, and so forth. There is a pattern here that allows me to quickly write this. Notice that if these are just regular hexadecimal values, then these are the magnitudes. But if these are signed, for signed information, anything over here would be considered negative. So when it comes to hexadecimal values, I know that anything that's 8 or higher must have a 1 sitting in front at the very most significant bit. Anything that's 8 or higher must have a 1. That helps me out because I can look at this value here and I know right away that that's negative because there is a 1 sitting in front of it. I also know that it's negative because of that, because there's a 1 sitting out in front of it. That's how 2's complement works. That's how complement notation works. It splits your group of numbers in half, and when you split binary numbers in half, the front values will always have 1 for the negative. So we do have a negative value that's here. So what that means then is we need to do a conversion on this. So if you were to invert these bits and add 1, knowing that the answer must be negative, you should get a value such as this, 28630. And then you'll see, I think in the notes, but also let me talk for a quick second about a shortcut. But this is, all right, so this is kind of a fundamental idea. It's important that you know what a 2's complement value is, when a value is negative or not and how to do the conversion. So I do want you to take a look at both, you'll see you'll get practice in a couple of different areas, both with the participation quizzes and also with this here. Thoughts or questions? Anything?
Professor?
Yes.
So just looking at the hexadecimal value, how do we know that it's a negative?
Well, this hexadecimal value, I know that there's a 1 that is the most significant bit if I were to place it in a group of binary values. And the reason I know that it's a 1 is because of the 9. That 9, or even if it had been an 8, if this is an 8, 9, if it's a 10, like anything over here on this side, guaranteed to be a negative, because there's no way I can represent 10, 11, 12, 13, 14, or 15 without the most significant value. I need anything 8 or higher has to have a 1 in the most significant bit.
Okay, thank you.
Yes, it's a really, it makes it easier to just kind of pick out negative values that are showing in a hexadecimal format really quickly. And the reason I know that it's a 1 just simply because when I look at every possible hexadecimal value as a binary, the only time that there's a 1 in front is when those values are 8 or higher for these different hexadecimal digits. It's a good question. It's really important. Just kind of, and when it comes, so much of what you do and what we do is just kind of learn the patterns that make our lives easier. And that's one of those patterns that when you see a hexadecimal stream of digits, that you're going to know that it's negative if that most significant hexadecimal value is 8 or even higher. Now, isn't there some, I don't see any questions over in the chat session. So these values that we're looking at, there's more than one way to do a conversion to get its equivalent kind of answer when it's negative. There is one way where first thing is that it's kind of a multi-step process, is that you look at this and you have to say, oh, it's negative. So my tendency is to go down somewhere and say it's negative so that I don't forget I have to go and write that it's negative, because you may just end up writing the magnitude. So now that I know that this is negative, I need to do the conversion. So here it was originally, flip the bits and add 1. 1 and a 1 is a 2. So the answer is a -2. So it's a multi-step process. Observe the bit. Make sure you note that it's negative, and then take those series of bits and figure out what the magnitude is. Now, there's also another way that we could have worked with this. There's a pattern that works like this. It says, given that we have 1, 1, 0, and we know that it's negative, what you can do, and this is always going to work, if you observe that it's negative and there's a bit there, just make that most significant value negative and then add everything else up as positive values. So this becomes -4 plus 2 will give you a -2. So there are kind of these two different ways of turning it into its equivalent. One is invert bits and add 1. And then this other way, take the most significant, I suppose it's using the most significant I'll use MSB. Use the most significant bit value as a negative, and then add. So I'll say, and add others, and add rest as positive. You can always use either one of these to determine what the value is. What this means then is if I take, and all of this is recorded, so you'll be able to come back and look at this. But if I take a number such as this, let's say that it ends up being, let's make up a value. This is a 5-bit value. Right away, if I tell you it's 2's complement notation, tell me what it is. You got to know that it's negative. The answer is going to be a negative value. So once you know that it's 2's complement, it's that. If I say that it's just simply unsigned, meaning that there's no information regarding sign, then it's a different value to be interpreted. If it's unsigned, it's a lot easier. 1, 2, 4, 8, 16, 16 and 7. I know that the answer is 23 if it's unsigned. If it is signed, then the answer is going to be 1, 2, 4, 8, 16. This is a negative 16 plus a 7, so that's going to be a negative 9. And so that's kind of the shortcut. Oftentimes, this will be easier to work with. That's the one. This is kind of the one shortcut. The other way is let's flip the bits and add 1. So let's go ahead and take all of these bits and invert them so it becomes 0. Flip all of the bits and add 1. So flip all of the bits, add 1 to, we're just getting the magnitude. We've already determined that it's negative. And then you end up with the magnitude here of being a 9. So no matter if you do it this kind of a shortcut way, where you just simply take this guy and make him negative and add the others as positive, you should get the same value that you would get from inverting the bits like we did here and then adding 1. So this is how we get the 2's complement. Flip the bits and add 1. Questions on anything?
A quick question, Professor.
Yes.
So we would take this same idea and apply it to, like, say, the first question that we're working on with that bigger value, or we could either do one of those two methods to get the decimal value.
Exactly. So now, and that's kind of why there's this long discussion, because I really just said, hey guys, this is the value. It's 28,630 as a base 10. And so you have a couple of ways of doing this. And there's usually just try to do whatever way seems easiest. When I look at this number, this first value, I don't really want to flip the bits. 1, it would be 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, and then start doing this math. I could do it. I could flip all of those bits and add 1, and that's legitimate. In looking at this, because there are so many zeros, it really looks like this one is going to be easier to determine its base 10 value. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. And then it looks like it's easier if I take all of these values. Let's do it like this. Maybe it might even be easier if I think I can simplify this even more. Put this into an eraser. If I do it like this, this is the radix raised to the 0 power, or the radix raised to the first power. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this answer looks like it's negative 2 to the 15th, and then plus 2 to the 12th, plus 2 to the 5th, plus 2 to the 3, plus 2. That feels far easier than flipping, the bits to get the answer. So both of these, that's the reason why I kind of just didn't go the long way with doing the standard invert the bits and add 1. I think this method here that I've just shown you is far easier. When you have this many zeros, and there's no, you can do either one, whichever one seems like it might be easier. And this one, I didn't want this to be a test on ability to add 16 numbers together. So notice that there were quite a few zeros here, and that was done intentionally to try to minimize kind of these mathematical errors by having fewer operations. So 10 to the 10th is one I have memorized as being 1,024. 10 to the 11th is 2,048. So if you add these numbers up, these are the ones that are easy, you should be able to get that same value. So those are the 3 values. Those are the answers that I'm looking for there. Questions, thoughts? And so you'll see, going back several semesters and in the lecture notes, some more discussion on that. But the ideas are pretty, hopefully, straightforward when it comes to going into binary to octal and octal to decimal. What the question that I used to get, and I get less frequently, is that someone will say, well, how do you take this and go directly to octal? I've tried to avoid that. I think that it's more error prone and it's time consuming. You can do it. There are videos out there that will, by others, and there are notes I think that I've placed up there that will show you how to do it. It's just not worth the work. We're going to automate this in a practical sense. So my preference, or my expectation really, is that you would just take the simple way. That's a 2. That's a 5. And that, I think that way is less error prone and it's quick when it comes to converting. So I'm not really expecting you to go directly from this to an octal. I'm really expecting you to go from this to an octal. And from this to base 10. And if you do that, I think it's going to be pretty straightforward. So if you get 3 or 4 practices in, it should be fine. Now, it asks you to convert this or extend this to a larger 32-bit value. So let's talk a little bit about what that means when it comes to sign extension. What that means is, if I have a number that is maybe simply, I'm going to choose some number here. This value is what, 1, 2, 4, and 8. So this is a 6. 4 and 2 are 6. If I want to sign extend this from 4 bits to 8 bits, because it's positive, right? So sign extension is what we can talk about when we're dealing with numbers that have sign information. This is positive. So if I take my 0, 0, 0, make 4 of those, and then rewrite the value here, 1, 2, 4, 8. In both cases, I have a 6 here. And if I look at this, even though I have all of this extra space here, doesn't matter. It's still nothing but a 6. So when I have positive values, sign extension is pretty easy. Sign extension, let's erase this, is just about simply taking the 0 that's here, and I can make it 8 bits, I can make it 32 bits. You just kind of continue writing more zeros and it doesn't change the magnitude. So sign extension for positive values is pretty straightforward. You just take the 0 and write more zeros. If I want to do sign extension, but it's maybe 1, 0, 0, 1. Assuming we just have a 4-bit representation, 1, 2, 4, 8. Can you tell me what this value is? It is negative. What negative value does it represent?
-7.
-7. So beautiful. It's -7, and because you now hopefully can do that shortcut where you say, oh, let me just make this guy -8, and then add the positive values. -8 plus 1 gives us a -7. So yes, so some of you will quickly see that there's a short, quick way of getting it. -7, you can it's wonderful that you can see it that quickly. And there's going to be a couple of you that say, oh, it's negative. Let me go ahead and write that it's negative. Let me flip the bits and then add 1, 0, 1, 1, 1. Oh, that's a 7. And then you go this. So that's it's a little bit longer, maybe twice as long, 3 times as long, but it works. So now that we know that it's a -7, my question that I'm asking really is, what does a sign extended -7 look like if we want to put it into an 8-bit box versus a 4-bit box? So this is a -7. And if I start off with a positive 7 and make him negative, so here's my positive 7 here. I know that this is positive 7. 1, 2, 4. 4, 2, and 1. So there's my that's a positive 7. If I want to get the -7, what I'm going to do is invert. Look at how all of those zeros become negative. I'm going to invert all of the bits and add 1 so that this becomes a 1, 0, 0, 1. But all of those zeros out front become 1s. So the pattern here that's important to observe is that our -7 here and our -7 here look very, very similar. It's just that there are these 1s that are sticking out on the front end. And that pattern will always hold. So when I want to take a -7 of some space and convert it into a larger bit space, all I need to do is duplicate the most significant bit to occupy whatever that space is. So I'm going to take him in 1, 2, 3, 4, and then this part 1, 0, 0, 1. So I have sign extended this so that I know that this is also a -7. So this is a -7, but it's using 8 bits. This is a -7 using 4 bits. The short answer, I think the takeaway from this is that if it's positive, extend it out to occupy the bit space. If it's negative, then duplicate the negative. So sign extension is really easy in that you're just going to take the most significant bit and make copies of him. So when I want to sign extend, oh, here's the other thing. Notice that when I did this sign extension, these ones that are sitting out here are the largest hexadecimal value. So this is, as a hex, this is going to be an F, and then this guy is always an 8 plus 1 is 9. And so this is a 9. So when I extend this out, it becomes a hex F9. And if I place this into a hex, it's a 9. So notice that there's another pattern there of putting F's in the front of this to extend this out, because those F's are really just 1s. That means that when I'm looking at 902A, if I want to take this value here and turn him from a 16 to a 32-bit value, my job is pretty easy. My job is to look at the most significant bit and then 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And now it is no longer a 16-bit negative value. It's a 16 plus 16. It's a 32-bit negative value. So all you will do is look at the most significant bit and make copies. Now, if this had been a positive value instead of an 8, if you look at some of the previous, I'll kind of make a change. I'll say either it's a value less than 8 or a value greater than 8, or 8 or higher rather. And that's going to test whether or not you kind of get this idea of how to sign extend. So if that had been a 7, that's a 9. Let's say that this is anything else. I could have just simply just keep it simple. This could have been a 0. If that had been a 0, then things change a bit. This is a 0, and then these are just zeros sitting out front. So you have to pay attention to what the most significant bit is when it comes to sign extension. So the answer for this is going to be, there were 4 bits, 4 bits, 4 bits, 4 bits, and then the original value, 902 and A. And so that's my 32-bit value. So that's sign extension. If it's a 1, typically it's just going to be F's that shoot out. If it's a 0, it would just be 0x, 1, 2, 3. Each one of these is actually 0, 0, 0, 0 as a binary, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, but I'm showing them as hexadecimal values. And so as a 32-bit hexadecimal value, it would look like, had it been positive, like had this been a 7, 02A, that's positive. Since 7 is the most significant bit, that's how you would extend it. So you have to know what the most significant bit is to know whether or not you're going to extend it with zeros or extend it with 1s, and therefore Fs. Let me take a look to see if there are any questions in this chat. So any questions on that? So if you look at maybe, once you do 2 or 3 of these, there's a pattern and there's a flow. The binary is going to come quickly, the 10, the 2, you'll see quickly how to do the conversion on each one of these. And from here, you'll say, okay, I remember the pattern. It's going to be a group of 3, a group of 3, a group of 3. You're going to say, oh, is it negative or positive? You know that it's negative. You have a couple of different ways of converting it. And then you're asked to turn it into a hexadecimal 32-bit. Just look at the most significant bit and decide how to copy that forward. And you'll see multiple examples. So do a couple of those and it'll start to flow pretty quickly.
Professor,
Yes.
so the only time we're gonna write a negative sign will be with the decimals?
Yes. That's kind of weird. Yes. The only time you're going to write a negative sign is if there's a decimal. So, so with hexadecimal, even though this is negative, I've never seen any kind of representation like this, 0x, f, 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 like that. That's just not conventional. It is a bit weird, slightly uncomfortable, but and a bit abstract. But yes, the only time you're going to do that is with a negative, with base 10. Good question.
Thank you.
Mm-hmm. Okay, so you have this, and it's on. I'm going to get rid of some of this because this won't apply to the second section that we're looking at. So this next part here gets into how instructions are represented and how they're kind of boxed. So you have a MIPS instruction that's encoded here. And then all MIPS instructions, there's a green card at the end of this. It's called green because normally it's a green kind of piece of cardboard that is in your textbook. So I often reference this as the green sheet. And so your instructions are formatted as either an R format, an I format, or a J format. So it's one of these 3 kind of boxings. It's a way bits are boxed. The R format typically means that you're working with register to register operations. And the J format, there are quite a bit fewer, but it's some type of jumping. So you want your instruction to jump to another label. And so you'll see that when you're doing jumps, you're changing this particular register that keeps track of where your program is. So generally, when you see a jump, you're changing something that's called the program counter. And that keeps track of which instruction in memory you're kind of working through. And I think it is just those 3. Yes. So every time there's a jump, you'll notice that the program counter is changing. So we won't get into, we'll look at for right now, I just want us to kind of focus on R and I formats. Let's go down a bit and look at what that box looks like. So the basic instruction formats, register to register kind of operations, right? Such as an add, which takes 1 register, and adds two, or puts into it the sum of two different registers. So T0 equals T1 plus T2 is what this one is doing. It's all register to register operations. So how can we convert that instruction to a number? We use bits 0 through 31. So there are 32 bits altogether. Notice that I can't just simply subtract these two to indicate, to show you how many bits there are. There are some number of bits that are used to represent a number, to give you a number that corresponds to the instruction. So each instruction has an opcode. Every number here that we see, either if it's two of them, the opcode is on the left, and you'll see why. If it's one of them, then it just simply is the opcode. But every number here that we see, either the left, if there are two, the left one is the opcode. And if it's just one, then that is the opcode. So every number will always, and every instruction will always have a number, an identifier that goes along with it. So the R-type instructions, let's erase this. First, every number, every instruction has a code, an opcode. Only R-type instructions have a function code as well. So this is really like a second tag to identify which particular R instruction there is. So each one of these, every time you see two, it's only going to show up for the R-type instructions. If you see two, it's only for the R-type instructions. But if you just see one, it's going to be for a different instruction. It's going to be an I. There is no function code. So these two together are opcodes and function codes, but in truth, only the R has an op and a function, an op and a function. Also notice that for all of the R instructions, they're always 0. The R code, the R formatted instructions will always have an opcode of 0. So that's really not enough to tell you which instruction there is, which one you're working with. If you have a 0, you have to go look at the other part of the instruction, the function code. But again, only R has both. So there are, over here, remember an R-type instruction is something like an add that has a T1, T2, T3. These registers, T1, T2, and T3, can also be identified with numbers. So register T0 is also register 8. Register T1 is also register 9. T2 is register 10. T3 is register 11. So I don't really need to use the name of the register. I could always just use the number. It's a little bit confusing because these registers serve purposes. So if I see an A0, I know that it's meant as an argument as part of a function. And if I see a V, I know that it's typically a value that's returned from a function. But if I'm just working with numbers, it's hard to see what's going on. So, but you can always use either one. They're both going to assemble / compile just fine. So as long as you have the $ and the number, it'll assemble, as long as they're values. And these numbers that you can use are values between 0 and 31. So we have 32 different numbers that you can use. So how does this come into play? This opcode has bits 26 through 31. Bits 26, 27, 28, 29, 30, 31. That's 1, 2, 3, 4, 5, and 6. You cannot subtract 31 minus 26 and get the number of bits. This actually has 31 minus 26, that's 5 plus 1 more. So this is actually 6 bits. 5 minus 0, if you include the 0, 0, 1, 2, 3, 4, 5. There is also 6 bits here that will be used to represent the function code. And of course, since we have 32 registers, 2 to the 5 is 32, so you need 5 bits to represent one of these numbers to indicate which registers you're working with. There's another instruction that does bit shifting left or right. We won't see that right away. When you add these up, 5 times 4 is 20, plus 12, that's 20 and 12 is 32. So that's a 32-bit value that we're going to get. Our instructions will be represented with 32-bit values. So let's go back now and look at what this value is here. Well, let's go all the way back up. So in order for you to know which instruction this is, you will have to look at the bits. So this is a hex 2. So I'm going to write this as, let's make this, so it's going to be a 0, 0, 1, 0. There's my 2. And then there's a 10, which is an 8 and a 2. So there's my A, there's my 2, and I need a C. So 10 is an A, B, C, 11, 12. So this is a 12, which is an 8 and a 4. And then this is an 8 here. And then I see 3 zeros, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's see if I can get some additional space here. And then the last one is a 10, which is an 8 and a 2. Remember, the opcode will always take 6. So it's kind of easy to remember the R format instructions because it bookends the left far end, the right far end is 6 and 6, and then 5, 5, 5, 5 in between. So the 6 bits, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. I now know what the opcode is. This opcode is 1, 2, 4, 8. Looks like the opcode is a 10. And if we look at this as though it's a hex value, I'm going to split it up into 4. So when your green card actually shows the opcode, those 6 bits, it shows it as a hexadecimal value. So that would be, as a hex, it looks like this. So I don't know how you can easily look at this because this only shows 4 nibbles, 4 bits, and then the other 2 have to be taken from the adjacent nibble. So you have to be really careful, but as long as you convert it to binary and grab the 6 bits, it will help you kind of figure out what the instruction is. So now that we know that the opcode is a 10 or hex 0A, I'm going to go back and use my green sheet to figure out which one of these is correct. So now we know what the instruction is. So that's kind of partly what it's asking you to do. Figure out what the instruction is. Can you see which instruction we're working with? So since the opcode is not 0, right, those 6 were not 0. So I'm not going to look at any of these. It's not a 0 based. So it's one of those singular. So it is not an R format. It's another formatted instruction.
The set less than immediate.
Yeah, it's a set on less than immediate. It's an instruction that's used to compare two different, to compare a register against a number, a register's value. So it's something that we're going to use for if less than, or branch if less than, branch if greater than. But in short, though, it's really just saying this is the instruction that we have. It's a set on less than immediate. And now that you know that, you also know something about the box. So number one, you know that it's an opcode of 10. And you also know that it is not an R format instruction because we didn't get a 0. So it has to be an I. Possibly could be a J, but we won't see that just yet. So if it's not a 0 that you came up with in those 6 bits, then that's what we have. So it's a set on less than immediate. Let me see if I can quickly go down to the end, page up. So the instruction that we have is a set on less than immediate. Let's go ahead and then it has a couple of different operands that it's working with. So so I'm going to have to be a little bit careful with giving you an instruction. I want to make sure that you've seen it somewhere in the lecture. And so it's there in video lectures, and you may not have gotten to this part yet, but the way this set on less than works, basically what it does, it takes whatever value, I'm going to use some different values over here, and then I'll go ahead and say register T0, register T2, and then a 5. The way the set on less than instructions work, it does a comparison between two different, like a register and an immediate meaning a constant. And if it's true, it will set T0 equal to a 1. If it's not true, it'll set T0 equal to a 0. So if it's true, it gets set to the true value. If it's false, it gets set to a false value. So that's how a set this guy if the first one is less than if the second one is less than the third, the T2 is less than the 5. There's another version of set on less than that's almost identical. I'll go ahead and put in the $, T0, T2, and T3. So it works the same way, where it looks to see if one register, in this case, not an immediate, but a register, is less than another value. And then it sets T0 based on whether or not that's true or not. If T2 is less than T3, this becomes a 1. If T2 is greater than or equal to T3, this becomes a 0. So that's what a set on less than and a set on less than some immediate value, an actual number, is doing. Questions? Now, here's one way to think about this, and this is actually how set on less than works. Imagine that this T2 has a 3, and then there's a 5. So what will T0 be? Will it be a 0 or a 1? Help. Is it true that this is less than that? And so it will set this to the truth of that comparison. Questions? Does that make sense? Okay, good. So it's going to be a 1. Here's what happens, and I'll just mention it, and I hope we can have enough time to look at the hardware to see what this is done. What it's really doing, if you want to test to see if one value is less than another, it's really simple. You use your hardware, you use your ALU, your arithmetic and logic unit, and you simply do a subtraction. 3 minus 5 is a -2. A negative value will always have his most significant bit set to a 1. So what set on less than is doing is really just taking the most significant bit and stuffing it into T0. So if it happens to be negative, T0 will always be a 1. Meaning that, so it's always set on less than, we'll do a subtraction. So that's what it's doing underneath, kind of underneath the hood. It's really just doing a subtraction, and it's pulling out the most significant bit and setting T0 to that most significant bit. If it's a 1, T0 just becomes the number 1. Now, if this had been, say, an 8 minus 5, this becomes a +3. And a +3 over here, 0, 0, 1, 1 looks like this. So is 8 less than 5? And the answer is no, 8 is not less than 5. So this becomes, and if T0 then would be a 0. Also, it's just taking the most significant bit of that subtraction and placing it into T0. So that's kind of the brief summary of what the set on less than is doing. Ultimately, you're just looking to see if one register is less than either another register or less than a particular value. So what we know about this is that this is an I format instruction. And then the I formatted instruction is boxed differently. The I format instruction they all have an opcode. He still has 5 bits for one register, 5 bits for another register. But if it has an immediate value, a number, then we have to have room to hold that number and represent that number in the instruction box. And so it uses 16 bits to represent that value. So if we have, so we're limited as to the largest value we can represent if we have a value here, or an 8, or a 38, or a 200, whatever that the largest value would be, right? It would be 2 to the 6, on the order of 2 to the 16. So it would be something on the order of 2 to the 16, and that's the set on less than immediate. And since it also has sign information, it's more like 2 to the 15 is the kind of the largest magnitude that we can work with. So it cuts it in half since we're actually dealing with sign related information, but I'll keep it simple and just use positive values here. So now that we know that it's boxed in this format, I want us to go back then and look at that series of binary numbers, extract 5 bits, because each one of those 5 bits will indicate the registers that we have here. So whatever those register numbers are, we're going to need 5 bits to indicate them. And then we also have 16 bits to represent some particular value that's here, whatever that number is. So I'm going to go ahead and extract that information out, and let's make this a different color so that you can see the divide. So it's 1, 2, 3, 4, 5. So now I know what this particular register index, this register value is. And if I go 1, 2, 3, 4, 5, I have another register. And then everything else, let's see, 4, 4, 4, and 4. Those are the 16 bits that represent the immediate value. So 1, 2, 4, and 8. I know that this is going to be a number 10. And so now I just have these two numbers here, 1, 2, 4, 8, and 16. 1, 2, 4, and 8, and 16. So this is a register, and then this is 16 and 6, 22. So I have two different, so I'm pretty much done here. It's either going to be register 22 and register 8, or register 8 and register 22. And I could ask you just to either leave it as a register number, or I could say go to the table and identify one register and another register. So there's one last thing. Which one of these is correct is what we need to figure out. So RS, this one registers register number 22, and then this one is register number 8, and we need to know which goes where. What's going to give it to us is that we have to go to the green card to figure that out. So I'm going to quickly drop down to the green card and look at what it says the logic is. In the green card, for the set on less than immediate, says that the guy who gets overwritten is RT. It's selected by the RT value. Generally, everything that gets overwritten is going to be in the RT or the RD box. So it's kind of like the destination or the target, the destination, there's target. RS will never be a register that gets written to. So RT is always the guy who gets clobbered, either RT or RD. And it all depends on, on the instruction. Generally with R registers, it's RD that gets clobbered. Generally with the I register, with the I instructions, it's RT that gets clobbered. There is a difference. So RT is the guy who gets clobbered. That means when I look at this, I know which one is the one who gets assigned a value. That's what I mean when I say it gets clobbered. It looks like register 8 is the one that gets assigned a value, and that value is the result of the comparison between those two. Whatever those, there's register 22 and there's a value of 10 since it's an immediate instruction. So it's registers 8 and 22. And I think in this particular one, it asks that you use register names and not just the numbers. So if I go back and I want to figure out what 8 and 22, what those registers are, I have to go back to the green sheet. Register 8, if I look at the number, register 8 is a T0. So register 8 and register T0 are exactly the same thing. Register 22, let's see, if that's 23, 22 must be a 6. So register 22 must be S6. So 8 and 22 have the names of T0 and S6. So T0 and S6. So what I'm looking for here is let's make this the register names. T0, S6, and 10. So questions or thoughts on that? So here's what it probably took us a good 20 minutes to go through that. It's a lot quicker the second time and even quicker the third time. There is kind of a mechanistic approach to this. So here's kind of what you do. You get the hex value. Knowing the hex value, you convert it to binary numbers. Once you have the binary numbers, you look at the first 6 values of the opcode. Now that you have the opcode, you're going to know if it's all zeros, it's an R. Otherwise, it's going to be an I. And later on, we'll get a chance to look at J. But you're going to look at the opcode to determine if it's an R, I, or J format instruction. Once you know that it's an R, I, or J format instruction, you know that it's going to be RSRT shift amount. It's either going to be this one for an R, opcode, function code. Each one of these would be 5 bits, or it's going to be an immediate, which still has an opcode. And it also has RS, RT, but that's all it has. Everything else just contains the number. So that's the big difference. Just knowing how to box those. There is the possibility that this value that is a 16-bit value here, this value is always going to be a 16-bit value, but it's possible that this could be a 900A. And so if it is a 9, or if it is a 10, and or even let's make this even an F. All of these guys, if this is a signed value in your immediate box, then this makes this a negative value. So it's possible for your immediate value in many, if not most instructions, to be negative. So if I look at what your green card tells you, let's go back to the bottom here. If you look at what the green card tells you, let's erase some of this. What the green card says is that it tries to give you some additional information that references one of the notes at the bottom. So you'll see the 2s, the 3s, the 6s, the 7s. Those notes reference information over here. So each instruction will have a note, and those notes are intended to tell you kind of how to interpret this information that's here. What is a 0 extended immediate? Now we know what that means, 0 extension on the immediate value. What is the branch address, or what is a jump address? The jump address. So for the sign, for this one in particular that we're looking at, it did say that we're going to do a set on less than by comparing one register to another value. It'll give you a 1 if it's true, a 0 if it's false. But it also says, in order for you to know more about this immediate value here, go look at note number 2. But it does also tell you that it's a sign extended immediate value. So if I go back down for my set on less than immediate and look at note number 2, it tells you essentially that it takes this field for the I type and just kind of takes all 16 bits. And then where it gets a little bit more interesting is that it says take those 16 bits, and if you were to put those 16 bits and look at the most significant one where they're labeled 0, 1, 2, 3, all the way up to 15, if you take that and look at them as though they're in an array, if you take that 15th one and then get 16 copies of them, that really is what we're doing with sign extension. Take the most significant bit and make additional copies. So take 16 copies of the most significant bit, and when you have the most significant bit, what you're going to do is use this, you're going to concatenate. So the comma tells you you're going to concatenate or just attach them on. So it's really saying, here's the procedure for how we do sign extension. I don't know if you have to dig too deeply into this, but it does tell you have 16 copies of the most significant bit of the immediate value, and this immediate value would be these 16 bits going across here. So it is sign extended, and it just really specifies what sign extension is. So be aware of that. It could always be this 16-bit value could be a negative value for your immediate. So I think I'm going to, let's see, let's quickly just point to some of these other things. Those two, and then the other elements here get into, well, we didn't talk about structs, but it does go into pointers and working with pointers. So the brief kind of, I'll let you look at this, but the brief way, let me just take a second to talk about this. What I typically do with this is that, and I'm really kind of asking you to do a trace. You have variables x, y, z. You also have a variable I, and then you have an array list. Notice that this list has exactly 6 elements, but if this had a 20 in here, and you only initialized 6, what that means is that everything else is set up with zeros. So I could have a 20, but not initialize them here directly, but because I've given some, it will complete the rest with zeros. But in this case, it just has those 6 values. So -4, 2, 1, 3, 5, 6. And there is a problem on the 3 most recent exams where a 20 is used as the initializer. So make note of that. List is the array, but it's also a reference to the very first element in the array. So when I declare this pointer v, v is also a pointer, so I can use v in that sense. When you say v++, that pointer moves from the -4 that's here so that it becomes v equals v plus 1. X equals 40. So each one of these variables, let's say it starts off with 40, and then x equals x minus 6. 40 minus 6 is 34. Y is equal to 8. Z is equal to x minus 5. So z is equal to 29. I was initially set to 2. And as I go further, the contents, so this says take 53 and assign it to list plus 3. So list is here, but if I do this pointer addition, so list is pointing to this one, list plus 3 takes us over here. So it's 3 hops, 1, 2, 3. So list plus 3 is exactly the same thing when you dereference this as list sub 3. So it's really just checking to see if you've taken a look at how we work with pointer notation. So list sub 3 equals 53. So it changes that to a 53. And we're almost done with this one. A couple of more. A equals the address of X. So A is a pointer that was declared. B is pointing to Y. And then this says the dereferenced value of A gets 6. And remember, every time we see, I can't think of when this is not true, when you see an asterisk A, you can say, well, what am I pointing to? Oh, it's X. You can just simply do a rewrite and say X equals 6. So it's taking the contents of that address and assigning it a value of 6. And then finally, well, down here it says Z equals X minus 3. So this kind of checks to make sure that you understand what's going on with how X has changed. So Z gets a value of 3. Y equals A plus B. Well, I'm going to go and look at what A is pointing to. A is pointing to X. I'm going to look at what B is pointing to. B is pointing to Y. So A is pointing to X. B is pointing to Y. So I think Y should be a 14 here. And then this one, X equals X plus plus, this I didn't like, but what I wanted to do was change this so that x equals the current value of I. So x, when it gets reassigned to the current value of I, x should have changed. Ideally, we want x to change to a 2. And then after usage, I then would become a 3. So this last one was checking to make sure that you understand that plus plus I is different than I plus plus. So this one will increment first. This one will use the current value of I and then increment it. So if I is 2, then what happens here is that this will become 3 because it will increment right away. And for this one, since I was 2, it will just take I as its current value and then increment it. So it really reads like you read a book from left to right. Do what's on the left first. So increment and then use it. Do what's on the left first. So take the value, current value of I, just take it, and then increment it after you've used it or assigned it. So there is a big difference between plus plus I and I plus plus. And so this is kind of a bit meant to be a bit of a check. This particular problem is undefined x equals x. It's a little bit weird, and that one should not have been there. And then print out the results. We can't do any. So look at the more recent ones here, since we're not dealing with structs. You'll see a better example. But this here is the same as take list sub I. That's the first line, and then I plus plus is what this is. So this is actually 2 lines in one when you do it like this. Take the value of I, use it, and then increment I afterwards. And that is there's a big difference between that and this. This is the same as increment I first. So this would be the I plus plus. And then use that newly incremented value of I. So the easiest way to step through this should be kind of maybe a 2-minute, 3-minute type of problem, is to set up a trace scheme of the 4 variables and the array. And you should be able to walk through this and change the values as you go through the code. Since we're running out of time, the additional information here has to be kind of placed on video, on a separate video. I'll do this quickly, and then maybe put up a video if I don't already have it that traces through this. Your data segment starts at a particular address. This problem says, here's the address. Well, the address that it starts with is 1001 and then all zeros. So I'm just going to focus on the all zeros. So this says assign a value of 0 to the first byte, or 2 bytes or 3 bytes, whatever this number is. It'll give a bunch of zeros to that. So that means address 0000 is nothing but a 0. This one is address 1, byte 1, byte 2. If I had more values, I would be able to tell you exactly what each one of those bytes hold. So I know what the address is of each one of these variables. This one starts at 1, this one starts at 2, and so forth. Here's the main idea for this one here. What is the address of this. This is kind of what this entire thing, a lot of what this is testing is this one idea right here. What is the address of this? Array 1 will contain, this symbol will contain the address. Is it a 3? Well, no. Here's the big idea is that anytime you have a dot word directive, the elements that come after it must reside on multiples of 4, so-called word boundaries. So this won't be on address 3, but it will be placed at address 4. And then this one here, and since he takes up 4 bytes, he's going to be 4, 5, 6, 7. This one will sit at address 8, address 12, 16, address 20. This one will sit at address 24. That's the start. And he takes up 4 bytes. So 24, 25, 26, 27. Those are the 4 bytes that occupies. This one sits at 28, 29, 30, 31. This one sits at 32. This one sits at 36. And this one sits at 40. That's the starting point. So that's all this one is really testing, is largely testing whether or not you get this idea of word boundaries. Bytes can be placed anywhere. Words can only start at multiples of 4. Here's the other big question. What address is contained here? Like, what is this guy's address? So don't forget, we stopped counting here.
45.
I think you're right. So 40, and he takes up, I think you're right. Oh, here. You got the right idea. You're off by 1. So he's at 40, and he occupies 40 and 41 and 42 and 43. The next byte, which can go anywhere, happens to be 44. And then this one, these 3 occupy 45, 46, and 47. So this is a little bit tricky. This is where I am most likely to make my mistake. And I think some of you also would do this. It will always be tempting to just start doing the shortcuts and forget that this is only the starting address. It will always be tempting. So it will be tempting to say, oh, he starts at 40, and then this guy goes to 41. And so be careful of that. This is just the starting address of and it goes 40, 41, 42, 43, and then this guy is a 44, and then 45, 46, 47. Oh, this was actually a little bit easier. So this one is 48. It makes it a little bit easier. Had I changed, so I'm going to pretend for a second that there's an F here, and that this is 45. Because this is part of that, this really kind of assesses whether or not this makes sense to you. Then when I go down here, this becomes, the A is byte 46. The B is byte 47. The C is byte 48. So bytes can be placed on any byte area, byte location. So here's kind of the big question. This is kind of everything right here. What is the address? What address would, this in this hypothetical one where I've added the F here, right? This doesn't exist on the actual, but you'll see it on the other. other exams. What is the address here? Meaning that if I were to just take this code and type it in, if I do a load address into register T1, and I'm putting in the address of val01, so load address here is going to contain whatever this value is. And so T1 is going to have 0x10011234. What is that address that it's going to contain? What number is it? So it has to be a multiple of 4, and it has to be 49 doesn't work, 50 doesn't work, 51, this has to be a 52. That's the big idea. That's kind of everything that I want you to be able to see where each one of these guys reside. And it will then, once we get comfortable to how words and bytes are laid out in memory, makes it easier and possible to kind of work with our data segment and do coding in MIPS. So that's good. And certainly a couple of you in the chat box are giving me the 52. This space just says put zeros into our data segment. So since this starts at 52 and it uses 53, 54, and 55 with this made up problem that I'm doing now, which is not the original, then this one here goes to 6 spaces of zeros, and those are at 56, 7, and then so 1, 2, 3, 4, 5, 6. And then this one here. So what would that address be? If you can type it in. And whatever that address is that you suggest, when you divide it by 4, it should be a multiple of 4. It should have no decimal point. It should have a remainder of 0. So is it 62, 63, 64, 65? So it has to be a multiple of 4, and this one would be 64. So that's all this is really trying to assess. If I go back in to finish this up and look at T1, where I did the address and it took val01, we said that it's 52. So T1 won't get a 52. T1 will get the entire address. And that address, 52, I just labeled them using kind of base 10 counting. But as a hex value, this is going to be 48 plus, well, 16 times 4 would be 64. 16 times 3 is a 48. So if I take my 52 and divide it by 16, it's going to give me a 3 with the remainder of 4. So as a hex value, these are going to be small enough where you can do this shortcut where you divide by 16 and then take the remainder. So I'm kind of taking a shortcut here. If you double check this and multiply 3 by 16, that's a 48, and add 4. So this value as a hex is shown here. So that is the actual address. It is 52 over, but it's a hex value that I'm showing. So since these numbers that I give you are going to be quite small, this will always work. Divide by 16 and take these two values and use them to kind of populate the hex value. And the other choice that you have for doing that, 1, 2, 4, 8, 16, 32, 64. The other way of doing this is to generate a 52. So I'll say that this would be too big. 34, all of those are too big to get my 52 in binary. This is the next number that is under 52. 32, that's going to give me 48. 48 and 4 is 52. So another way of doing your conversion is to actually take your 52, convert it to binary, or convert it to convert it to binary. And then what you'll see is that as a hex, 3 and 4, you can do a conversion that way as well. So you could take your 52 and convert it to hex. But I think it's far easier just to look at how many multiples of 16 go into the first digit, and then use the remainder to get the second digit. So that's what this is looking for. Given that we have this bit of code, load address, and a load word or an add immediate, what are these values? I think it was there's example code that you can use to kind of program this in, or you can actually copy and paste from these and play with it in Mars and test your understanding. And then there are other online. Let's finish with this, and then I have to. Okay, and then we'll tie it up here. So this one right here, translate to MIPS. A sub 5 is going to be set to J. You're given that J is stored inside of register S2. So I'm doing this one because this is a little bit easier. So what I'm going to do is a store word. And where will I store it? Store word takes information and stores it going from the left to the right. So I'm going to store J, which is S2, and go put him into an address. This address is 20 bytes away from the beginning of from the start of the array. Because this is an integer, where each integer occupies 4 bytes, since I'm looking at sub 5, this corresponds to a position or a value that is 4 times 5 away from the beginning of the array. So for the array, we're using A sub 0. The way store word and load word both work, what they do is they take what you see in parentheses here, and it does the addition of the value of these two values. Oddly enough, it uses the parentheses to represent the fact that these are kind of being dereferenced. So it takes the 20 plus the A sub 0, and it accesses that particular memory address. And that's how it stores it into the data segment. So that's what this one is doing. It stores J into this address. And all we have initially is just the beginning of the array, but we also know how many bytes away A sub 5 is, since these are contiguous array elements. And the most recent module that's put up goes further into that. Finally, J minus 1 looks like we're going to have to pull something out. We're not putting something into an array, we're pulling it out and then storing it. So I know that part of this code here is going to require that I put something into J. And since I'm getting it out of memory, I'm going to have to figure out what those values are. But this is my J So my stand-in for J is S2. So I'm assuming that that value has already been established to represent J, or that register has been. So let's see. What I first need to do is whatever the current value of J is, I'm going to subtract 1 from it. Or at least get the equivalent of 1 minus that. So I'm going to do this. Since J is here, S2, this will say that T0, this temporary value, is going to be S2 minus 1. So I have not changed J because this is not J minus minus. It does not ask you to change the value of J. So be careful with that. We can't change it at this point. So we just have a holding spot for it. Now that I have it, I want to multiply whatever this index is by 4. With binary numbers, when I shift left, it's equivalent to multiplying by 4. So if I shift these binary values just once, for example, I shift left and fill this in with a 0, this binary value that was a 5, when I do a shift left of the bits, this 5 becomes a 10. So shifting left once multiplies by 2. If I shift left twice, it's equivalent to multiplying by 4. And if you look at this, you'll see that there's a 4 and a 16 to get a 20. So shifting left twice is the same thing as multiplying by 4. And since I know that my index will always be multiplied by 4 to figure out what the starting address is, then what I want to do is a shift left logical on this value here, T0. And I want to shift it left twice. That's how I'm going to multiply by 4. And I'll take that result and hold on to it. So now I have the index multiplied by 4 inside of T0. And then now that I know this will give me the offset from the start of the array, I'm going to add that offset to the starting address of the array. And so what I have here, I'll just reuse T0. I have the starting address of that particular indexed element, J minus 1. I have the address of that array. So I have the address of that array element. I have the address of the beginning of the array, and I know how far apart, how far away that particular element is. He's always going to be 4 times the index away from the beginning of the array. So I can use that address and I can extract from it the value. And now I have in this J, S2 is going to be the dereferenced value. So this gives me A sub J minus 1. So there's a pattern here that once you do a couple of these, it becomes a little bit easier to see what's going on. I'll always just do something like this where I do a shift left logical, and then I reuse this, and then I reuse it again, this temporary register. So I'm going to, for a brief moment, kind of ignore the add. This is the pattern here where when I'm using a load word or getting something out of an array, it's going to be an S, an A, and an L. It's a SAL, S-A-L, that I frequently will do to get things out of an array. That pattern will save you lots of time and effort in thinking about how to get something out of an array. Unless your array is a solid constant value, right? Because then I can just say 5 times 4 is 20. I don't have to shift it left. If it's not a constant, if it's an index, if it's a variable, you're always going to have to do a kind of a shifting or multiply by 4. And then once you have it multiplied by 4, you're going to add that value to the beginning of the array. And then once you get that sum of the array and the offset, you're going to use your load word or possibly your store word. But I'm trying to show this pattern here where you get a variable that has the index multiplied by 4. And then once you get the sum, you take the sum and use that. So there's this pattern that makes it a little bit easier to think about. So there are these two patterns. Look at the T0 becomes this element, whatever this value is, this register, he's going to ultimately be used to extract a value out of memory. And so that pattern is shift left, add it to the base of the array, or the first element in the array, and then use a load word to extract it. So I'll give you a chance to ask questions on that. So I'll post this that we've talked about here. That actually, we were able to get through quite a bit. This is an instruction that we won't look at just yet that deals with branching. So there's a branch if equals and so forth. So and there's a jump involved in this. So we haven't had a chance to talk about that. So I won't give you anything that looks like that. Questions on anything, dig into it, and then let's either send me something this evening or tomorrow if you have any questions, but you'll see at least 4 or 5 copies, similar structure. These are the types of things that I want you to be able to do. Certainly get practice with it, and you'll have at least 24 hours to go through it. So you won't be under the crunch of trying to get it done in 75 minutes. But now's the time to start asking questions. Once the exam starts, I won't answer questions that are kind of directly tied into, unless there's any confusion, but I don't want to answer the exam problems. So, but look at the practice exams, and that should get you in pretty good shape. All right, I think you guys are ready to knock it out. Just make sure, this is really just practice and patterns. So make sure you do it. It'll be time well invested. Your final exam is coming up quickly. What I typically do is just kind of pull from previous quizzes and pull from the midterm. So if you put the time in and do well, the final exam should be kind of a straightforward, you've already practiced it. So put the practice in now and it'll pay off for both. You'll find it's time well spent. All right, guys, we'll stop there. It was a long one, but
Thank you, Professor.
All right, have a go at it, and please ask questions, and we'll see where we end up. Take care.